Hey, what is going on everyone? I'm Wicked, welcome back to my channel. In the first part of this chapter, I showed you a comprehensive explanation on how isolates work inside Dart, tackling some of the fundamental differences between synchronous and asynchronous events. In the second part, we also got our heads into how we can work with single or multiple synchronously generated values. Today, it's finally time to check the third and last part, covering up the asynchronous particularities of this chapter. Please pay as much attention as possible to this tutorial as you'll learn about two of the most important concepts of Dart language, futures and streams. So without further introduction, let's get right into this tutorial. In the previous part, I started the tutorial by mentioning that a synchronous operation is more like a task that needs to be taken care of before proceeding to the next one, right? Well, can you guess what an asynchronous operation is? Not surprising at all, an asynchronous operation is still a task, but the major fundamental difference compared to a synchronous task is that we're not restricted to wait for the task to finish until we can get to the next one. In an asynchronous environment, we can process multiple tasks while the current one is still being taken care of. Now, the best analogy I could make for this tutorial regarding these asynchronous operations is that we, as humans, can use some of our tools to work asynchronously in a really efficient manner. Say for example you want to watch a documentary on TV, iron some of your shirts, and wash some other clothes. It would be literally 3 times more efficient if you do all of these tasks simultaneously instead of doing them one at a time. Therefore, you can set the washing machine to wash your clothes while you iron your shirts in front of the TV watching the documentary. In the previous tutorial, we saw this really important table. In an asynchronous workflow, a single value that we know is going to be calculated and retrieved later on has a type of future. On the other hand, 0 or multiple values that we know they're going to be calculated and retrieved later on have a type of stream. You might imagine that streams, compared to iterables, can emit all values asynchronously, while other tasks are being taken care of in the background, while iterables only emit the values synchronously, one after another, while no other task can be executed in the background, thus highlighting the fundamental difference between synchronous and asynchronous workflows. We're going to tackle futures and streams in great detail in the following minutes, so let's start with futures first. So, when thinking of a future, you must think of it as an asynchronous event. We talked about those in the first part of this chapter. Back then, we observed that a future, compared to a synchronous stable defined type, brings some uncertainty into the game. It's just like the future versus the present in the real world we're living in. We don't know what the future will reserve us. Therefore, the asynchronous event denoted by a future can be represented as a box. This box can be under 4 states during its lifetime. It can be unprocessed, meaning that it's still waiting in the event/microtask queue to be processed by the event loop, uncompleted, a state where it's been processed by the event loop but has not yet been retrieved the promised calculated value. It can be completed with an answer in which the promised value arrived with an expected type, and it can also be completed with an error in which the promised value didn't arrive and instead it threw an error. A synchronous event, on the other hand, can be represented as a box with only 3 of these states: unprocessed, completed with a value, or completed with an error. The uncompleted state is not possible to be achieved on a synchronous event since synchronous events have to be completed before moving on to the next one in line. I hope this really makes sense to you right now. So, in order to understand all of these particularities, let's go ahead and power up VS Code and see how we can play with those futures. The best way to start this approach would be to take a look at some of the most popular constructors of a future and perhaps see how all of those execute and set their events on either the event or the microtask queue. The first one in line is the default future constructor. This is probably everyone's choice when creating a future. If we go ahead and check out the implementation, we can notice it accepts a function as a parameter and this function can have a return type of either future or a normal type. Most of the futures will accept both of these types as the computation parameter. This is why we have two examples for each of these constructors. Also, we can actually see that Dart creates a new future out of this and uses timer.run to run the complete method with the computation function we provided. In this scenario, Dart has actually put the workers to work in order to complete that box we just talked about earlier. Another important future constructor that we're going to use is Future.delayed. As you can see, it is really similar to the default future constructor. The only difference being that the future computation will be executed after the amount of time you provide as a duration parameter. In our case, I set it to 1 second, so only after 1 second the computation will run and the future will try to complete. Note one important deduction from this. A future.delayed with a duration.0 is equal to the default future constructor, as it won't wait for a specific period of time until it executes it. Normal futures, like the ones we discussed until now, are being set as events on the event queue inside the isolate and not on the microtask queue. Next up, we have the Future.value constructor. This is a really special constructor as it won't take a function as a parameter, but rather, as its name implies, a normal value or a future value. Future.value is used whenever you want to complete a future with a value immediately. In this case, it's like printing the value directly, but in an asynchronous manner. In this specific case, the event is actually placed on the microtask queue since it has priority of being printed immediately. This is obviously achieved whenever the value passed as a parameter is completed, like in our first case. However, it can also take in a future as a parameter. In this case, our line of code is actually equivalent to writing this future with the closure returning 6. Believe it or not, Dart will interpret this line of code as being this default future constructor since the Future.value constructor can't complete with a value immediately. Future.sync is really similar to Future.value in a sense that instead of taking a value as a parameter, it takes a closure, a function. As you can see from the implementation, if the closure evaluates into a value that's not a future, it simply calls the Future.value constructor with the return value of that closure. Otherwise, if it is a future, it simply returns that feature. So, to sum up, our Future.sync constructor here is equal to Future.value of 7. This is what Dart is going to process at the end of the day. Our second Future.sync constructor is simply equal to a normal future constructor since it cannot calculate it right away. Again, the only difference is that the Future.sync takes a closure while Future.value takes a value as a computation parameter. Future.microtask constructor, on the other hand, is a little bit more different than the previous two. If we browse its implementation, we can see that it uses the schedule microtask function. This function will actually place the event denoted by the calculations inside of it right on the microtask queue. So, compared to the previous .value and .sync constructors, that resulted in a default future constructor if the computation parameter was a future. Thus, on the event queue, this being a microtask will result in a future, but that future will be placed on the microtask queue instead of the event queue. The rest is pretty much the same. At the end, for spicing things up a little bit more, I have added another set of default future constructors. Note that each of these futures will eventually complete in either a value or a future. Therefore, print a number from 1 to 12. This number representing the order in which these lines of code were called in the first place. We know that when running a program, the isolate will synchronously read the code in the main file line after line. So it will go like 1, 2, 3, 4 up to 12 this way. For learning purposes, we want to know the order in which Dart will print the result of this program. What you might also have noticed is this function that we call after we create the future. Then, actually helps Dart know what to do with the future or the box when it completes. Therefore, inside this function you can have a closure you can use to do something with the response you receive later on. We're actually telling Dart to register a callback to what's going to happen when the value will be received. In our case, I set up the print closure so that it will actually print the received value. Basically, if we had not placed this then function there, all of the incoming values would have been lost because there's nothing that can listen to when they're coming. It's like a bus arriving at a station. If nobody's waiting for it in that station, it just leaves and is gone forever. As I said before, futures may not always result in proper values, but can also end up in throwing errors. As a result, we also have a onError method we can chain next to then, in which we can decide what to do if we got an error as a response to a future. We also have a whenComplete function we can chain. This is called whenever the future returns a value or an error, no matter what. It's more like the finally statement in a try-catch block. Having this in mind, what do you think the output of this program will be if we run it right now? If you watched the first and second part of this chapter, you should be prepared to simulate it. I'll give you 10 minutes to think about it. You can pause the video and try it by yourself. However, note that, as I said at the beginning of this chapter, these may seem like simple stuff, but you'll actually see from the example above how difficult these simple lines of code can get to interpret. Also, if you find this tutorial really useful and you appreciate the way I teach these concepts, please make sure to share the video, hit that like and subscribe button, and consider hitting the notification bell so that you'll know when I post a new video. Also, make sure to follow me on Twitter at Let's Get Wicked. This is where I'm at most of the time. Having that said, let's get back to our simulation. Let's go ahead and run the program by typing in the famous Dart run command and check the output. Now, if you got the same output as the one showing up on the screen, congratulations, you absolutely master futures. You're an absolute genius. But if you are like me a couple of days ago, you wouldn't be able to get this result not once in a million times. Now, in order to understand where you were wrong, I want you to pay attention to the real simulation process, as it is very detailed and a little bit mathematical, I would say. So, in order to start the simulation, what I would recommend you to do as a primary step is to construct the event and microtask queues, as well as the output for the program. I will also add another auxiliary queue that will represent the order in which Dart reads the lines of code one by one. Notice we also have two synchronous calls, one marking the start of main and one marking the end of it. The lines of code are read by the isolate from right to left, just like the event loop does. Okay, so the first line of code is the synchronous print call. This is processed directly by the event loop, and as a result, start is printed into the output zone. The next line of code brings us to the first async event, denoted by a future, which is going to complete with a closure evaluating in 1. As a result, the event loop knows that sometimes in the future, the answer to this future will arrive. Therefore, we will place 1, which is the result, on the event queue. Then we move to the next line of code, denoted by this future, which is going to complete in a closure evaluating into another future. Dart interprets this and knows that sometimes in the future, a little bit later than the previous event, the response to this future will arrive. The result of this future being another future will mark it as f of 2 for ease of understanding. Again, note that the order in which the events will be processed later on is from right to left, as the event loop is somewhere in the right part of these queues, processing events one by one. Moving on to the next line of code, we can observe we're investigating what's going to happen if we have this Future.delayed constructor. Well, in this case, we can see that the future will be created after 1 second. So we know that in both of these lines of code, the response will come a little bit later on into the event queue. The rest of the lines aren't delayed, so most probably these two events will always sit at the end of the event queue, just because the rest of the futures will be processed much faster compared to this 1 second. So let's go ahead and set them at the end of the event queue, just like we did with the previous features. But this time we need to remember that these will happen long after the previous two ones. So I'll space them out a little bit. Next up, we have this line highlighted by the Future.value constructor. As I mentioned earlier, since this value is a standalone value and not a future, it means that the Future.value can complete directly right away. As a result, the event won't be placed into the event queue, but rather into the microtask queue so that it has higher priority. As a result of this, we'll place 5 onto the microtask queue. The next Future.value constructor has a value of future sent as a parameter, and according to what we discussed earlier, we know that the event loop will treat this as being a normal future with a closure ending up in returning 6. As a result, 6 will be added to the event queue, but bear in mind it won't be added at the end of the queue, since those two events are delayed by 1 second. It will be assigned just before them. The exact same thing happens to both Future.sync constructors. The first one, being a closure ending up in returning 7, can complete the future right away, so it will be placed on the microtask queue. The second one, being a closure ending up in returning another future, cannot complete our future right away, so Dart will process it as being a standalone future and will place the 8th event on the event queue again before the last two delayed events occur. Now, moving on to the microtask part of our program, this is where things get really interesting and unique. Bear in mind, in this case, both of these resulting events will be placed on the microtask queues, no matter what. As a result, first and foremost, 9 will be placed onto our microtask queue, followed by f of 10. Again, pay attention, even though this is a normal future, it's constructed with a Future.microtask constructor that will schedule it on the microtask queue no matter what. Moving on to the last two normal futures, those will be placed again into the event queue, but before the last two delayed ones. So we'll have an 11 and an F12, right? Now the event loop scans the first line of code, sees that it's synchronous and prints it directly as an output. At this moment, all lines of code were read, the microtask and event queues were established, and currently our console should only print start and end. Now the event loop will start processing the next batch of events, but as we know from the first part of this chapter, the events on the microtask queue have priority, therefore it will process those first. So it will process 5, print 5, process 7, print 7, process 9, print 9. Then it will get to this future that will have to process. As surprising as it may sound, the result of this future, which is 10, won't be placed onto the microtask queue, but rather on the event queue because it's a normal future. It will also be placed before these two delayed events. As you can believe, all the operations we've processed until now happen in milliseconds. As a result, we'll put it just right here. Now, since the microtask queue is empty, the event loop can move on to processing events from the event queue. It will process 1, print 1, then receive this future, process it, and place 2 again before the two delayed events at the end of the event queue. Then it will process 6, print 6, process 8, print 8, process 11, print 11. Then it processes future of 12, just like with the previous ones. 12 is set at the end of the event queue right before the two delayed events. Now the event loop will process 10, print 10, process 2, print 2, process 12, print 12, and process 3, print 3. Finally, at the end, it will encounter the future of 4, process it, and place 4 at the end of the event queue, being the last event. Then, the event loop will process this last event and print 4. Both of the queues are now empty, and the isolate terminates the program. And this is the final output of this program. It seemed easy at first, but as you saw, there were some pretty tricky events you had to consider. Now, to clear things out even more, I have another example for you. Can you guess what the output of this program will be? I'll leave you again a couple of minutes to try an experiment, so go ahead and pause the video and simulate it by yourself. So this time we'll speed up things a little bit. I'll create both of the queues plus the output right away and we'll process the events line by line. The first line is a synchronous print statement, so the event loop will process it right away and print 1. Then the next line will schedule a microtask with a closure returning 2. As a result, we'll place 2 onto the microtask queue. Then we have a Future.delayed constructor, which after a delay of 1 second will create a default future with a closure returning 3. As a result, we'll place 3 into the event loop, but again, take in mind this is going to be delayed quite a while. Then we move over to a really interesting feature. So we have this feature chaining multiple thens. What you need to know about this is that, as we talked, the first then will be executed whenever 4 will arrive in the event queue. So, for the moment, we'll only place 4 into the event queue, but before 3, which is delayed. We shall keep in mind that this 4 is linked to the other then events. So, we'll move to the next line, which is again going to place 9 on the microtask queue. Then, we'll have again a nested future. This time, when 10 will arrive down the event loop, we'll know we need to process these events too. Moving on to the next line, as before, the event loop will scan it and place 13 into the event loop, but before the delayed event. Then we have another microtask, which will place 14 into the microtask queue. And finally, the event loop receives a synchronous call, which is going to print 15 directly into the console. So, for the moment, only 1 and 15 will be printed into the console. We have elements in both of the queues, but since microtasks have priority, we'll process those first. So, the event loop will process 2, print 2, process 9, print 9, process 14, print 14, and the microtask queue is emptied. Now, onto the event queue. It will process 4, print 4, but remember, 4 was chained with multiple then callbacks after it. What you need to know about these callbacks is that they will be executed immediately in this case. They won't be enqueued into any of these queues. As a result, it will move to the first then, print 5, then execute the entire callback inside the next then function. In this callback, we'll print 6 and place a new microtask 7 on the microtask queue. We have one more then callback to execute, which is going to print 8. Now, if we analyze the queues, we can see that the microtask is not empty anymore. As a consequence, the event loop will have to take the next microtask events and process them until the queue becomes empty again. So it will process 7 and print 7. Now, moving on to the next event, we'll take 10, print 10, and since this is linked to this then callback, we'll make sure to execute it before moving on to the next event. As a result, we'll process this first callback, which is going to return a future. Then, as a result of this, we'll need to place f of 11 onto the event queue, before the delayed event, of course. The trick here is that we're able to process the next callback only after the event loop processes the 11 event, because that is the moment f of 11 will be completed with a value of 11. As a consequence, the event loop will move on to processing the next event from the event loop, which is 13, and print it. Then it will receive f of 11, then place 11 into the event queue before the delayed event. When the event loop receives event 11, it prints it, but remember it was linked to a then callback a couple of moments ago. That then callback would get executed right now, resulting in printing 12. The next and last event is being processed, ending the workflow by printing 3 and terminating the isolate process. This is the output we should receive, and as you can see, it checks with the one resulting from running the Dart program inside VS Code. I want you to observe that not everything related to asynchronous programming is easy. Whoever said that futures are really easy to understand and practice is lying. It will definitely take some time to get used to how everything goes where, but at least for now you have a strong foundation you can rely on. So, right now let's head back to our first example. We understood the concept of a future. which is more like an empty box waiting to be filled with the result of that computation, right? But at the moment, if you pay closer attention to our program, apart from printing the result when it comes down one of the queues, we're doing nothing more than that with the result we've been waiting for so long. Let's say we have a variable a. We want the result of this future to be assigned to this variable a. Suppose this calculation here is really important and is done asynchronously in the background. The intuition will tell us, well, we can assign the value into the then callback here, right? So that whenever the callback is executed, we'll just write a equals value. This is 100% correct. In this case, after the future is completed with value 1, a will be assigned to 1. But obviously, if you created this variable, then that means you're going to use it somewhere else, right? Let's say all we want to do with it is print it, a line below, so that we can check if our callback works as it should. What do you think this statement is going to print? It should print 1, right? Well, surprise! If we go ahead and run the program, Dart throws us an exception, telling us that local variable a has not been initialized yet. Why is that? Didn't we initialize it when we completed this future here? Yes, the variable got initialized when the future completed. That's 100% true. But the variable we don't know from this equation is when is this future going to complete. The truth is that nobody knows when a future will complete, because this is the whole idea behind a future. It will eventually complete, but sometimes in the future. Nobody knows when, not even the event loop. A couple of minutes ago, yeah, we were able to estimate a little bit the order in which the futures were going to complete, but what we didn't know is when they were going to complete. As a result, what we're actually doing wrong in this program is expecting the future to finish sometime before we call the print a statement, right? But what's actually happening in the background is Dart processing the future, then registering a callback to execute whenever the future completes, even though it doesn't know when the future will complete. As a result, it will move on to the next event. This is the principle of asynchrony. Therefore, it will process the next event, which is synchronous, but it notices that the value we're trying to print hasn't been yet initialized, since the future hasn't been yet completed. This is probably one of the most important async concepts to be understood. Then you might say, well, there must be a way to wait for the future to complete before we assign the a variable to the value, right? Yes, you might have heard of the await keyword. This is absolutely its only purpose, to wait for a future to complete. So let's go ahead to see how we can achieve what we want with the await keyword. Well, first of all, we can get rid of this then callback for now. We have this standalone feature. Right now, after removing the then function, nobody is listening to it anymore. It may complete, it may throw an error, nobody cares. But we want the value it completes with to be assigned to our variable. Well, in this case, all we have to do is to assign it directly, just like this. But you see, this is a feature that's going to complete with an integer, and this is a standalone normal integer. Therefore, we need to await for this feature to complete in order to assign it to our a variable. As you can see, Dart isn't happy about this. In order to use await, we need to mark the function we're calling it as being asynchronous, and we can do that by writing async right before the body. Now, an async method will always return a future, since, well, similarly to how we're waiting for a future to finish before assigning its value to a variable, others may also want to access the return value of our function. So we'll need to let them know that the content inside of it will come in the future. Now, if we go ahead and run the program, Dart will process this feature, wait for it to finish, assign it to the a variable, and then move on to the next event in which it will print its value. But then you might say, doesn't this defeat the entire purpose of asynchronous workflows, waiting for an event to finish before we can get to the next one? Yes, this is correct. Using await will pause the entire thread until this feature is completed. The idea here is that the computation function running in the background runs asynchronously. We literally saw this a couple of minutes ago. However, if you want to know when exactly the future will complete, you will have to use await. and this will indeed make the workflow a little bit more synchronous. This is why if you really depend on the result of a really high computational async process, you may want to spawn another isolate and make that one process it while you're managing other events. Now, what about the then callbacks? This means they're useless in this scenario? No, they're definitely not. They can be used as an alternative way of coding features. We can actually use it to assign the a variable to the value with a then callback. But still, if you want to know exactly when that feature is going to be completed, we'll have to await for it. So yeah, overall, I hope you understood how asynchronously returning a single value works with features. But now it's time to get into something even more complicated. Actually, if you entirely understood the futures part, streams will look much more straightforward and easier to grasp. So, compared to futures returning one single value in the future, streams, similarly to iterables, can return 0, 1, or multiple values. The difference between streams and iterables though is that streams values are not returned synchronously, right away, one by one, but rather asynchronously in the future. In order to understand this easier, let me show you one of the simplest streams you can implement. We're going to use the periodic name constructor to achieve this. Basically, without looking into the documentation, what this line of code actually does is emitting values from 0 to infinite with a delay of 1 second between them. If we run the program right now, we can see that nothing gets printed. This is because, just like in the case of a future, the values coming down the stream need to be listened to. If futures had the then callback, well, streams have a similar function called listen. As a result, we can call listen on our newly created stream, so that whenever a new value will be emitted down the stream, this listen function will be called, and the closure inside will be executed, therefore printing the value. If we run the program again, right now we can see the stream in action. Just notice how each value comes down the stream one after another. This is the concept of a stream. Now, in order to see that this is actually happening asynchronously in the background, why don't we create another stream, in the case of which we'll emit negative values from 0 to infinite every 2 seconds. Now, you can clearly see, if we run this program, that for each 2 positive values, we get a third negative value. This is because the first stream is emitting values each second, and the second one is doing it every 2 seconds, while they're both running asynchronously in the background. And observing what we previously discussed about features, we know that features complete with a value in the future, right? As a result, we can actually construct a stream from a bunch of features using the fromFeatures constructor. Note the asynchrony support again, since if we set these 2 features as a parameter to the constructor, they will be printed again in the right order, since the future.value will complete first, therefore it will be added to the stream earlier than the normal feature. I want you to observe how everything starts to make sense right now. Generally speaking, when we talk about a stream, we should think of it really as a stream of water. You can think of the values emitted down the stream as being some ships containing those values. Of course, those ships are added to the stream by some authority. They can't simply appear out of nowhere, and they obviously need to have a destination dock where someone expects them, aka listens to the values coming down the stream. The authority adding them to the stream is the StreamController, while the dock expecting every boat to arrive is a StreamSubscription. Know that, by default, only a single StreamSubscription can listen to a stream. The stream needs to be a broadcast stream so that multiple subscriptions can listen to it. Having all of these components in mind, you need to know that you can use them to create a stream of your own. For example, the first object we need to create is the StreamController instance. As I said, this is the authority that's able to add ships down the stream. By creating a StreamController, we're actually linking it to a stream, because a StreamController will always come packed with a stream. As you can see, we can actually access it by typing in StreamController.stream. This is a getter returning the created stream. So currently we have initialized the stream and the StreamController. But how is this controller going to add ships with data down the stream? Well, for this, we need to use the add method from inside the StreamController class. We want to achieve the same behavior we had with our Stream.periodic constructor. As a result, we'll create a timer object with the help of periodic constructor. This timer will execute this callback for every second, for an undetermined amount of time in our case. So, before the timer runs, we can create an integer value and assign it to 0. Then, for every tick of this timer, we can add the current value to the stream by using the StreamController.add method, and then increment the value. Remember from long ago, if we had ++ value instead, then the value would have been incremented before being added to the stream. So we implemented the StreamController, the stream, and programmed how the controller adds new values down the line. But now we need to set up the dock listening to the stream. As a result, we'll just type StreamController.stream.listen, and for each of the received values, we'll print them just as before. Now, if we run the program, we can observe we have the same functionality just as with the Stream.periodic constructor. But at least now you know the functional components of a stream. Note that this listen function returns a StreamSubscription, just as we discussed, so we can actually assign it to a variable. But now, Dart shows us this warning, mentioning that we haven't written a line of code that's going to close this subscription when they won't need to listen anymore to the stream. This is a vital concept to be understood. When you create a StreamSubscription object, it won't stop listening to the stream until you'll manually cancel it. Ideally, you'd want to cancel it after you're not interested in the values of the stream anymore, or whenever the stream won't simply emit any more values. So, for example, in our case, if our value ends up being 5, then we'll cancel the timer as well as the stream, as you can see from the code right now. As a result, the stream won't emit any new values anymore, but the StreamSubscription object will still be listening to the stream, which can lead to memory leaks. So, if the value becomes 5, then we'll also cancel the StreamSubscription. Now, the warning is gone and everything works just as it should be. What I want you to also understand is that by default, only a single StreamSubscription can listen to our stream. If we try to create another one listening to it and run the program, Dart will throw a bad state exception mentioning that this stream has been already listened to. In order to have multiple StreamSubscription listening to the same stream, the stream needs to be a broadcast stream. As a result, we must create a StreamController with the help of the broadcast constructor. Now, if we go ahead and run the program, we can see that both of these StreamSubscriptions listen to the same stream, therefore printing each value twice. So I hope you kind of understood the main components of a stream. But now, the same question arises, just as in the case of futures. Do we know exactly the moment when a value will come down the stream? Maybe we'll need, for example, to retrieve the biggest value emitted by the stream. How are we going to do that? Obviously, we'll need to await for the values of the stream in order to calculate which one is the largest, as we don't really know when each of the values will arrive to the StreamSubscription. We will comment the StreamSubscription implementation for the moment. So we know that in order to wait for a single future to complete, we use the await keyword. But remember, a stream will return multiple values. As a result, we will need to use an await for structure. So, for each value we're waiting for, we can calculate the maximum value directly. And when the stream will get closed, then the await for will also exit, and Dart will print the max value on the screen. We can also achieve this again by using the for each method directly, so that for each value we retrieve, we calculate the new maximum, but don't forget to await for it to loop through all stream values. You see, streams are really similar to futures in many ways, as instead of returning a single value in the future, streams may return 0, 1, or even multiple values in an asynchronous manner. Streams are a huge topic to discuss, and it would take me ages to do so. I'm trying to show you the major concepts so that you'll start the journey of understanding them with a solid foundation. You need to know that we're not done talking about the methods on how you can create a stream of data yet. I want you to remember from my previous tutorial how we were able to create an iterable by using a synchronous generator function. Well, in the same manner, we can create a stream of multiple values by using an asynchronous generator function, as we're going to see up next. So, creating an asynchronous generator function is absolutely similar to creating a synchronous one, just as we saw in the previous tutorial. This time though, the return type won't be an iterable, but rather a stream, and the keyword won't be sync star, but rather async star. Let's say for example we want this async generator function to generate values from 0 to 4 onto the stream. To achieve this, we'll have to use a standard for loop from 0 to 5 and then use the same yield keyword to add the values down the stream. This is just like we were calling the StreamController.add method before. Obviously, since this generator returns a stream, we can call the listen method on it and print each of the elements we will retrieve. If we want them to be a little bit delayed, we can actually await a Future.delayed with a duration of 1 second inside the async generator. It's that easy. Oh, and also, similarly to how a synchronous generator could yield another generator with the yield star keyword, the same happens in the case of an asynchronous generator. We could, for example, yield another stream within our main stream, just like this, and everything will work just as expected. I want you to understand and see by yourself how abstract and interesting streams can get. They can be really useful in multiple scenarios, and they represent the foundation of reactive programming, a design paradigm that relies on asynchronously programming logic to handle real-time updates to otherwise static content. We'll use streams all the time in future Flutter tutorials. If you want to learn more about the power of streams, I would highly suggest you to go right ahead and check out the Eric's Dart package, a package that will provide so much more functionality to the already impressive Dart Streams API, and perhaps let you understand more concepts about what can be done with streams. Having this said, I think it's finally time to end this Dart sync and async chapter. I hope you understood everything in great detail, at least the foundation you need to perfect your skills in becoming a Dart and Flutter expert. We have finally arrived at the end of this amazing Dart from Novice to Expert tutorial series. With everything we learned in this course, I will create a small and interesting command line application that will help you understand and practice every concept in detail. However, this tutorial video, as well as other future updates on Dart, will only be available to those of you buying the full Dart course I'll launch in the following week on Udemy, so stay tuned for that. I want to thank everyone for watching this amazingly long series of learning Dart from a novice to definitely an expert level, and I hope you really enjoyed every single tutorial I've made. Thank you. As always, if you like this tutorial, don't forget to smash that like button, subscribe to my channel, and share the video with all of your friends and colleagues in pursuit of top tier development. Until next time, as always, take care, Wicked is out, bye bye.